Hello folks, I'm Dr. Amit Vasudevan, a senior researcher at Carnegie Mellon University Software Engineering Institute. I will be presenting an OSD-funded exploratory research project that has been ongoing for the past year. The project aims to achieve incremental and compositionally verifiable security for CHIC-centric cyber physical systems. We use the acronym CHIC to describe commodity, heterogeneous, interconnected computing platforms. The CHIC software stack has been identified as one of the cardinal software stacks of not just the present, but as well as the future of software systems. The research problem we are attacking is insecure DoD CHIC-centric cyber physical systems implementations. This problem stems from the fact that the CHIC stack is heterogeneous by nature. We have disparate hardware platform architectures, multiple software layers, and millions of lines of software spread across those layers with diverse development pedigree. This opens up a plethora of attack surfaces. An effective solution to this problem must meet three goals: be provable, so we can have assurance on the security delivered; allow DoD to procure and maintain such provably secure CPS implementations in a cost-effective manner; and last but not least, preserve existing functionality to the maximum extent possible, or be innocuous, stemming from the NASA innocuity definition. Current state of the art is polarized across two axes. On the one hand, there are approaches that offer security targeting cost-effectiveness and innocuity to some extent, but are not provable otherwise. On the other hand, there are approaches that offer security by writing and verifying an operating stack from scratch. However, these approaches are not cost-effective or innocuous when applied to the CHIC stack. This is exemplified by a quote from our industry partner, Dr. Delbert Chrisman, VP R&D at Autonodyne, a US Air Force Skyborg and Golden Horde Vanguard program awardee, where he shares the frustrating development experience of his team with solutions similar to SEL4. We asked ourselves, can we combine the goodness from existing opposite ends of the state-of-the-art spectrum to get provable, cost-effective, and innocuous security on CHIC-centric CPS implementations? Our answer is CHIC stack implementation security via incremental, composable, and development-compatible verification. Our vision for this broad strategy has been published in the prestigious ACM SIGOPS Operating Systems Review Journal. For this project, we limit the security scope to on-platform secure sensor access, that is, integrity protection of the CPS application, sensor hardware driver, and trusted path between them. In other words, an adversary cannot inject malicious CPS sensor data into the application stack. There are three high-level pieces to our strategy. First, interface-confined object abstractions that form resource closures or monitors. We call them Uber objects. Second, runtime protected group of Uber objects called Uber object collections. They are bootstrapped by a platform root of trust entity that endows memory protection and secure call routings. Third, CHIC implementation level assume guarantee reasoning that allows us to mesh Uber object executions with other unverified system components. Let us now dive into our technical approach, starting with Uber objects that form design time building blocks. Uber objects allow principal entry, interruption, legacy code, and other Uber object invocation. This allows assume guarantee style reasoning at the implementation level and allows new Uber objects to be threaded with previously verified Uber objects, while incurring verification cost commensurate only with the new Uber object being added. The Uber object assume guarantee programmatic abstraction also unlocks the potential of being able to use multiple verification techniques to prove object properties, as opposed to a one-size-fits-all methodology, such as refinement proofs in SEL4. So we are provable and cost-effective. Uber object collections are runtime building blocks comprising a protected group of Uber objects bootstrapped by a platform root of trust entity. Root of trust entities can be implemented in hardware, software, or a hardware-software hybrid, depending upon platform capabilities. Call routings within and across Uber object collections are enabled by sentinels, which allow caller-callee mediation and support flexible implementation, such as regular calls, hypercalls, etc. Uber object collections, root of trust, and sentinels together enable retrofit at a fine granularity at any layer of the CHIC stack on a commodity hardware platform of choice. Makes our approach innocuous. Putting it all together in the context of our secure sensor access property, we can now use an off-the-shelf platform, an open source root of trust entity such as a microhypervisor, add two Uber objects, one for the sensor driver and the CPS application component, implement and verify these Uber objects separately, and compose everything together to essentially carve out a trusted integrity protected path between the application, sensor driver, microhypervisor, and sensor hardware as shown for a GPS sensor in this example. Our research and development so far has been focused on the root of trust entity, a small yet crucial piece of our grand vision. Today, we have an open source compositionally verifiable microhypervisor root of trust framework that supports x86 and ARM platforms and is able to support a CHIC stack running the Linux operating system. We've had some initial success with extensions at just the microhypervisor root of trust layer. However, when we go end-to-end through other CHIC stack layers like device drivers, applications, we have a bunch of open research challenges we have yet to conquer. Further, these research challenges have to be handled across 4 dimensions: security, verifiability, performance, and retrofit cost, the SVPR trade-off. This research project forms a foundational exploratory step towards this next big leap of end-to-end incremental and compositionally verified security across multiple CHIC stack layers by focusing only on a subset of the open challenges for a single security property. The SVPR trade-off eval will help us test our hypothesis, which is to see if our solution and technical approach presented so far will indeed be able to provide incremental and compositionally verifiable security for an off-the-shelf CHIC-centric CPS platform. Our off-the-shelf CHIC-centric CPS is a Rover platform running an ARM CPU and the Linux operating system. Our focus is on the secure on-platform sensor access property and implementation and verification of the driver and CPS application Uber object. We compare our technical approach to the base system without Uber objects in the context of a mission functionality following a predefined waypoint. Our collaboration with Autonodyne, a US Air Force Skyborg and Golden Horde program awardee, allows us to pose research questions and identify success criteria for the SVPR trade-off eval that is practical and meaningful. We deem the project successful if mission is completed in a time window comparable to the base system without Uber objects, mission is completed successfully even against an attack, example, injecting malicious sensor data. We are able to verify and compose Uber object subproperties on Uber object implementations across the root of trust and sensor drivers. And last but not least, we are able to do this in a development compatible and functionality preserving manner. We will now proceed to discuss the details of our SVPR trade-off eval in the following slides. Our security objective is to evaluate that we are able to achieve secure sensor data reads on our platform. Our eval metric is a simulated memory integrity attack, where the attacker overrides the sensor data before it reaches the CPS application. Our success criteria for this objective is that the rover with Uber objects completes the mission while mission fails on the base system without Uber objects. We designed and implemented secure sensor access mechanism using root of trust backed Uber objects for the sensor driver and the CPS application. The root of trust protects Uber objects so they cannot be directly manipulated by any other system component. We use HMAC for sensor data integrity and authenticity between the sensor driver Uber object and the CPS application Uber object. Our solution effectively prevents sensor data integrity attacks. Time for a demo. This is a PyRover demo with Uber objects and the Uber XMHF microhypervisor root of trust. The PyRover is essentially a 4-wheeled counterpart of the NASA Mars rover DIY kit. It has support for 3 sensors that help with line following, light following, and object avoidance. It has the same smarts as a NASA Mars rover DIY kit, the Raspberry Pi 3 board, Linux operating system, and a Python-based mission controller. Missions can be line following, light following, or traveling while avoiding objects. Here is the PyRover following a circuit using a line following sensor module. As you can see, the line following sensor module has 5 color sensors that essentially capture the position of a 1-inch black strip and actuates the wheels accordingly to stay within the lane, indicated by the black tape on the floor here. The circuit can be of any kind. It can be straight, curved, circular, and the car will automatically back up, reverse, etc. to make sure it keeps following the line. Now we demonstrate an on-platform memory attack that essentially prevents a line following functionality. In the terminal in the top left corner, we first log into the PyRover and start up the line following functionality. In the bottom left terminal, we now simulate an attacker who has gained access to the platform and who executes a memory attack on the mission controller process to override the line following sensor data values. This is done by overwriting the sensor data buffer on the heap. And as you can see, the result is that the car stops following the line and rams into the wall without being able to reverse or do anything else. All right, it's time to own the attacker. We first bootstrap the Pi rover with sensor and application Uber objects backed by our microhypervisor root of trust. The bottom left terminal shows the microhypervisor boot up serial log showing that the root of trust has initialized on the Pi rover and in turn has booted the Linux operating system. In the top left terminal, we log into the Pi rover and check to see if the microhypervisor root of trust has initialized successfully with a simple test hypercall. In this case, we get a hello world success message showing us that the microhypervisor root of trust and Uber objects are in place. Now we ensure that the Pi rover line following functionality works as before with the added root of trust and Uber objects. In the left terminal, we once again log into the Pi rover and start up the mission application to perform line following functionality. And as you can see, the rover continues to follow the line and circuit as before, but it is now operating with the microhypervisor root of trust and Uber objects which preserve existing functionality. All right, the final act. Same on-platform memory attack on the Pi rover is now prevented by the microhypervisor root of trust and Uber objects. The rover continues to follow the circuit even in the presence of an active attack. Top left corner terminal, we start up the rover as before for line following functionality. In the bottom left corner terminal, we launch the same memory attack as before by simulating an attacker who is manipulating line following sensor data values on the mission control process memory. However, in this case, instead of the car derailing and ramming the wall, Uber objects protect sensor data buffers, preserving the line following functionality. This is indicated by the data about debug messages you see on the top right terminal window that correspond to unauthorized writes detected on the sensor data buffers and disallowed. Our verifiability objective is to evaluate if we can achieve composable, provable invariance towards our security property. We evaluate this objective by formally modeling the CHIC-CPS stack via TLA+, the temporal logic of actions, and code-level specifications on the driver and application Uber objects. Our success criteria is that we are able to automatically discharge the security invariance in a development-compatible fashion. Our approach pipeline starts with the CHIC-centric CPS system model and invariants for memory safety, memory integrity, and control flow integrity, our trifecta property. These are encoded in TLA+ with mechanized proofs that show that these invariants hold in a distributed setting. We follow that up with a hierarchical mechanized proof of the invariants in the distributed setting, which show that the invariants are indeed inductive, which means they hold for all possible execution traces of the system. Once this is done, we can now routinely discharge those invariants on the C and assembly code of the CPS application and drivers using sequential verification tools. Time for another demo. This screen shows the TLA Plus model we've developed modeling the CHIC-centric CPS platform. It is a very low-level model of the CHIC platform, including access to CPU cores, memory load, store, and execute, and execution of Uber objects and other legacy code. To the best of our knowledge, this is the first time TLA Plus has been used to model a system at such a low level of granularity. The model is written in PlusCal, which is then transpiled into TLA Plus temporal logic specifications automatically as shown. This example shows how we encode memory safety invariants within our model to show that Uber objects only access memory regions allocated to them. We then use the TLA model checker TLC to automatically discharge those invariants on the model. While we do this via the toolbox in this example, we can use the command line as well. We then prove the invariants are indeed inductive, that is, hold on all execution traces of a CHIC-CPS platform. We do this using the TLA proof system, or TLAPS for short. TLAPS mechanically checks TLA plus proofs, which are described in a hierarchical and declarative manner. These are inductive proofs having an initial state and next state relations and cases for each of those. These are converted into SMT formulas that are then passed to a backend SMT solver for proving. In our example, we use Z3 as our backend SMT solver. Finally, the invariants are encoded at the source code automatically using a sequential verification framework and code level specifications. We use FRAMAC and ACSL specification language for this purpose. The resulting code is then passed through a verification engine, in this case, abstract interpretation, which then proves the invariants valid or invalid as shown. Our performance objective is to evaluate if we can achieve acceptable performance towards the security we have retrofitted. Our evaluation criteria is a set of benchmarks for CPS application and sensor I/O. Our success criteria is that our rover should be able to complete the mission without the attack within time window comparable to the base system without Uber objects. Our anticipated memory overhead was 8 to 15%. We collected results over 10 labs. As you can see from the first and second bullet points, the system with the root of trust and Uber objects performs very close to the base system. The third bullet shows that we can actually complete the mission even in the presence of an active attack. However, the mission time increases from 19.8 seconds to 24 seconds in this case. Our CPU utilization for this is about 3%. Our final objective is that of retrofit, which evaluates the effort to incorporate Uber objects into the existing code base. Our eval metric was source lines of code and function variable metrics differential on driver and CPS application code. Our success criteria was that it was comparable to refactoring effort that developers encounter similar to interfacing with existing operating system APIs. Our SLOC changes involved adding 25 lines of Python code to cope with smoother turns on our wood floor testbed, and 200 lines of C code for application and sensor driver regarding refactoring as Uber objects with the HMAC as well as interfacing to the root of trust via a library. The entire effort took about a month for a developer who was new to the rover code base. We published a couple of papers with one work in progress paper, and all our artifacts are open source on GitHub. In summary, we've had a lot of wins in this project. We were able to realize root of trust batch security with Uber objects on existing CPS ecosystem with minimal performance and developer retrofit to protect against memory integrity violation class of attacks. We were able to prove concurrent memory safety in the TLA plus model of our system and discharge corresponding invariants on the driver and CPS application code automatically. We want to get other DoD programs involved and will work with you to mitigate any risks in such a transfer. Future work involves scaling in the presence of multiple sensors and sensor types and investigating proof engineering tactics that will help us maintain and evolve mechanized proofs in addition to the already development compatible code level verification. This research project is important in the context of DoD CPS, which are becoming key to all the modernization priorities in DoD. Integrating baked-in provable cyber protection into these systems will be critical to the success and much better than layering patches later on. We have a multidisciplinary team comprising SCI research staff collaborating with CMU scientists with synergistic expertise required to carry out our research project. Autonodyne serves as a DoD industry partner providing us with feedback. Thank you very much.